In the last problem, we had an acrobatic diving gorilla. And at the end of the problem, we needed another equation. We appealed to kinematics, but we had to study uh, the system and start noticing, uh, what wasn't moving and all. And so determining the conditions to help us get an extra equation is often very confusing for students. And so we're going to do two problems here that are very helpful for just developing those skills. So this problem itself looks mindlessly simple, and it's not hard, uh, but it has some good concepts in it. So what I have is a trapeze. So here's a slender rod, weighs 4 pounds, hanging by two ropes. And at time t equals 0, somebody cuts one of the ropes. All right? And what we want to do is figure out what is the tension in this one. It says T2. That must be T2 because the tension here, once you cut it, 0. So that's boring. All right, so this is 3 feet. This weighs 4 pounds. What's the tension in this cord after it's cut? So let's take a look at before it's cut. So here I have basic free body diagram. Tension 1, tension, also tension 1. It's symmetrical, so whatever tension's in this rope will be in this rope. So T2 really represents the state after cut. All right. So we have 4 pounds in the center coming down. And if you sum moments and sum forces, what you come to the conclusion is that each one of these, just because of symmetry, there's 2 pounds here, there's 2 pounds there. Now, as we cut this rope, let's just think about what's happening here or equivalently there. If I cut this, all right, this is hanging. As this is cut, is this bar moving? At the instant that it's cut, no. Once that force is away, it'll start to accelerate. All right, but the initial angular velocity of the rod, once it's cut, will be 0. All right, but let's think about this point A. All right, if you look initially here, are there any forces in the X? No. If we cut this cord, that tension will disappear, but there's no forces in the X. Therefore, there can be no acceleration along the X anywhere here. It's impossible. No forces in the X, no acceleration in the X, because the sum of forces equals ma. All right. And this thing, we have gravity, so this cord's coming down. There would be no basis. We have 2 pounds here, 4 pounds there. There's no basis for it going up. And because of the constraint of the cord, it can't go down. So if you look at A, a sum of force, it can't go up or down. It can't go in the X. So there's no acceleration in the X, no acceleration in the Y here at A. It can't be. All right. Well, if there's no acceleration in the X or the Y, how is this point even going to move? It can't move in the X. It can't move in the Y initially. So this is going to be a center. All right. It's going to be this is a motion constraint. So the velocity here will be 0. Once you cut this cord, initially this isn't going to be moving, but there'll be no acceleration here. This will be a center of acceleration. Okay? This point can't move. So what's going to happen? The rest of this, okay, you've got a force here relative to this point that can't move, you're going to have a torque. It's going to start to go like so. Okay? This bar will start rotating down initially. Okay? A is a motion constraint. We're going to need that. Acceleration of A initially is going to be 0. There's no forces in the X, so AX must be 0. And because of this cord coming down, it's hanging, it can't go down any further, the acceleration in the Y must be 0. Acceleration at A is 0. Therefore, everything happens relative to that. All right, so let's cut the cord. So we'll have a tension 2 going up, and here's 4 pounds going down. So whatever that tension is minus 4 will equal mass times acceleration. We'll figure it out. If we sum the moments about g, okay, So we'll have T2, it's 1.5 feet out, because this is 3 feet total, will equal I alpha. So that's right here. So T relative to the center is going to go clockwise, so that's negative, minus T2 times 1.5. 1/12 ml squared is the mass moment of inertia. And then alpha, we'll assume that's going to be counterclockwise positive. Let the signs all work for you. All right. And if we look at that, though, we have there's an unknown, alpha is unknown. We need another equation. And here's where we can appeal to kinematics. We know the acceleration at this point A is 0. All right. And so what we want to do is relate the acceleration of A and the acceleration of G. All right. So the acceleration of, we could have put, I guess, a few more details in here, but the acceleration of G is going to be, let me just add this in, acceleration of A plus the acceleration of G relative to A. All right. And we can then add, so what is this piece? Oops. This will be alpha cross R minus omega squared R, where we're going from A to G. Right? That's the extra piece we can add in right here. So acceleration of A is 0. Well, that's boring. When we first cut the cord, just like with the gorilla, omega is 0. So all we're left with is alpha cross R. All right. So if we assume AG is positive, alpha cross R works out to be R alpha. R is 1.5. You can do the vector work if you want. I'll leave that to you. But here's what we get. AG, which would be in the Y, is 1.5 alpha. Okay? So now we have 4 equations and 4 unknowns. I'll let you go through the math and solve it, but we come up with the acceleration here. You can go follow the math. The acceleration of the center of mass for the bar is minus 24.2 feet per second squared versus G is 32.2. So we have about 75% of a G. And solving for T, cutting it takes us down from initially 2 pounds down to about 1. It works to be 0.994 if you go through it. 1 pound, close enough for me. Now we're going to do this problem one more time. And we're going to change the nature of the ropes. So here we have ropes hanging down. What if we had springs here? So we were hanging by springs. How would that change things? Well, let's see. So here we have the problem. Same problem, so this is still 3 feet, 4 foot rod. Except now, A and B are hanging from springs. So picture we have springs here and then we have ropes coming off the springs, or we could have the springs directly connected to the rod. All right? So in any case, we have 2 springs here, and I want to find the acceleration of A. All right? Now before, A couldn't move. It was hanging by a rope. Okay, it couldn't go down any farther. It had no basis of going up. There were no forces in the x, so it couldn't have acceleration in the x. So the acceleration of A before was 0. Evidently, now it's not. Let's think why. All right. So at t equals 0, somebody comes in and breaks the connection right there from the spring here to that end of the rod. Okay? So initially, the tension in both sides, we're assuming that both springs have the same spring constant. If that's the case, then the tension in both of them will be the same coming off here, or the force. If there's a cord hanging from the spring down to the rod, there'd be a tension in the cord. In any case, the force of the spring on each side would be 2 pounds. All right. And then somebody comes in and breaks off T1. So now we have the following free body diagram. All right. Now here's the important point here. How do springs work? Okay. A force in a spring is equal to K times X. There's a spring force, and then this is the stretch in the spring. I'll put an FS for the spring. So because there's a springs here, this has moved down. So when you cut this, there's still a tension in this spring. This piece has moved down. Okay, it's a little bit stretched, extended here. So therefore, since this point is still stretched, there's still a 2 force-pound based on the stretch in the spring. All right, so we know the tension. We didn't have to really figure it out. It's just whatever it was initially. After you cut it, bam, this is still 2 pounds, 1.5 feet off, 4 pounds here, the weight of the rod. Let's analyze what's going on. So if we sum forces in the x, it's boring. There are no forces in the x, so acceleration in the x everywhere is 0. Summing forces in the y, we have 2 pounds here up, 4 pounds here down. Okay. Just a second. And that equals mass times acceleration. There's no unknowns other than that. We can solve for it. So acceleration of g is minus 16 feet per second squared, so it's not as much as it was before. If we take the moments about g, right here, I'll put a g in here, equals I alpha. So we have 2 pounds, 1.5 feet away. That's looking clockwise, so minus 2 times 1.5 equals mass moment of inertia, 1/12 ml squared, times alpha. Solve for alpha, we get 32.2 radians per second squared. And so we know acceleration of g, we know alpha. Now, once again, initially, there will be no rotation. The moment you cut that, the initial angular velocity here will be 0. So we need acceleration to start developing angular velocity. All right. So omega 0, alpha is minus 32.2, so we can figure at A, knowing the acceleration of g, then we can, using relative acceleration, move over to A. And that's what we have here. Acceleration of A is acceleration of g, minus 16, plus alpha cross r, which we have right here, minus omega squared, but omega 0, so that term wipes out. And we have the acceleration of A is actually equal to g. It's moving up quick. All right, so that's the end of these two problems. The next problem I'm going to give you is a former exam problem, final exam problem actually, and one that didn't go well. So hopefully we can learn from it and not have the same mistakes happen again. I'll see you there.